Go ahead, Chris.
Okay, so are we live? Okay, I didn't see a countdown or anything. Sorry about that, everybody. Hello and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. My name is Chris McCubbin. I'm a data scientist and software developer with experience in developing complex systems and analytics. I'm currently with Amazon AWS on the detective team. Previously, I co-founded a big data security startup named Squirrel, which was since acquired by Amazon. I've been a member of the ACM Q Case Study Steering Committee since 2014. And for more on my background, you can look at the current slide. Look at the widget on your screen. So for those of you who may be unfamiliar with ACM or what it has to offer, here's a little bit more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen currently. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. The ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. So let's see here. Sorry. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. If you are experiencing problems with the slides or audio, refresh your browser or close and relaunch the presentation. Since this is question and answer, we encourage you to submit your questions to Theo during the talk. Please type them in the Q&A box at any time and click the submit button, and I'll organize the questions as Theo speaks, and we'll try to get to as many as possible. There are also some previously submitted questions that we'll be asking. The session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of this presentation, you'll see a survey open on your screen. If you could, please take a minute to fill it out to help us improve our tech talks. You may also open the link to the survey at any time from the resources window. You can use Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACM Learning. We'll be watching for your tweets. We also have a community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during today's session. So today's presentation is ACM Q Case Study Q&A, Always On Time Series Database by Theo Schlossnagle. So this is Q&A based on an article that was published a little bit ago with the same title. So Theo is the founder of Circonus and continues to be its principal architect. Prior to that, Theo founded OmniTI, which has established itself as the go-to source for organizations facing today's most challenging scalability, performance, and security problems. He was also the principal architect of the Momentum MTA, which is now the flagship product of SparkPost, an innovation that is transforming the email software spectrum. Widely respected thought leader, Theo is the author of Scalable Internet Architectures from SAMS, contributor to Web Operations and Seeking SRE from O'Reilly, and a frequent speaker at worldwide IT conferences. Theo is a member of IEEE and a distinguished member of the ACM. He serves as co-chair of ACMQ and holds the elected position of ACM member at large. Theo, welcome to the Q&A.
Well, thanks for having me.
Yeah, glad you can make it here. And so today we don't have a presentation. We're going to move directly into questions and answers. So for the first question we have today, we're gonna pull one from one of the ones that we were submitted previously. So Theo, could we today talk about the flexibility of time series databases and maybe how you might use one in the context of like a larger system, maybe in concert with an RDBMS or a graph database or something of that nature?
Sure. I think this is sort of like an evolutionary question of databases in general. So there's a strong argument that you don't need anything but a relational database if the features are rich enough, because you can certainly store event data and relationship data and do graph queries and do time series queries against kind of a traditional relational database. Most of them have pretty comprehensive functions around doing that. The problem is that we found this with graph databases probably 15 years ago, that when you start generating a tremendous amount of like material value out of questions that would go against a graph system, having a database optimized to answer those questions, increases the capability set there. It allows a lot more freedom of innovation. And I think that the same thing is true with time series database. So 15 years ago, jamming in a normal database was pretty reasonable. But then when you started to see the growth of machine-generated data, both the breadth of the data and the kind of the high frequency of the data, the economics around running a relational database to do time series data was poor, right? So if you're going to send 1 trillion measurements in and they cost nearly nothing to generate, they also need to cost nearly nothing to store and analyze. And that just wasn't the case without kind of turning the problems on its head. So with that, you're building purpose-built solutions to handle extremely high-frequency telemetry data. As you'd imagine, a lot of the things that you gain in performance and efficiency, you lose in generality. Right, so they become non-general databases. They're not very flexible in their use cases. So you're not going to be issuing graph queries against a time series database typically. So what you see is you either get a relational database that kind of does everything okay, or you get purpose-built databases that do specific things extremely well. And as engineers, what we do all the time is we integrate things, right? So if you have a system that requires a graph database and a time series database and things like that, you kind of just try to do them all until the economics or the capabilities don't match, and then you start to optimize and remove generalization. So I mean, I think that like the more advanced the specific database, like a graph database or a time series database like ours, becomes, the less general it becomes, and the more you're required to integrate that through coupling with other existing systems.
So kind of along those lines, is it your feeling that we don't need like one monolithic database that does everything, but maybe like different databases that are specialized and talk to each other?
I would say that my argument is stronger in that we can't afford one monolithic database to do everything. It's just not capable. It's not good enough, right? So if I'm going to send you 1 trillion measurements over the next, say, minute, which is not unreasonable in a large scale system where you have something generating and a device generating, say, 1 million events per second. You've got a couple thousand of those devices spread in each of your data centers, and you've got lots of data centers. It's very easy to get up into the kind of astronomically high numbers. And it turns out a fast device can generate a million measurements a second, and it costs you a penny for that second. So it can't cost you more than a penny to store, retain, analyze that data. So the idea of using a general purpose database for that becomes intractable. Like, it's just not financially feasible to have a return on investment there.
Right. Yeah, that makes sense. So, once you make that decision to kind of have time and sensor data, maybe sensor points as your focus of your database, time becomes like a really big deal, right? So maybe we can talk about time for a second. time formats and how you store time and how you reason about time. It's something you have to decide pretty early on in the design of a database. And we've seen these very famous failures, I guess you could call them, of time formats in the past, like Y2K and the upcoming Unix epic issue. So what did you do in your database to maybe future-proof that? And what do you see as kind of the way that time formats and how we reason about time is going?
Yeah, I think throwing back to a speculation of history is interesting here. There was an old statement that said you can correlate the fall of empires with the changing of time zones, right? The idea of changing how people count time was usually indicated the oncoming demise of a reign or a rule. Like time zones are probably the worst thing that has ever happened to people who have to deal with time. So I think that time zones are incredibly important for people to understand context and time on the output side, on the the user perception, user experience side, even potentially through the querying side. But from a generation point of view, I mean, I think ideally what we would really like to do is understand when the birth of the universe it was exactly to the right femtosecond or attosecond, and count the number of attoseconds since that. And that would be it. So we don't have a beautiful reference point like the birth of the universe, but we do have this magical time of January 1st, 1970 that we all tend to agree on. So having that fixed reference point and counting time since then ends up being an incredibly robust way to kind of unambiguously specify time. So I think that using Unix epoch, regardless of what system you're on, is something that is unambiguous. And I would say that there's some really interesting insight, I think it was accidental, that happened with the old APIs in Unix around get time of day. There's a time val or time spec later on that has two structural components. One of them is the seconds since 1970. And then the other is the offset in either microseconds or nanoseconds. So I think what we've sort of adopted internally is this idea of number of seconds since 1970, which we use as a 64-bit unsigned value. And then from within inside of a second, the number of attoseconds offset. And that allows us to specify any point in time precisely enough, more precisely than humans are able to measure it scientifically. So I think we're future-proofed, at least for the rest of my lifetime. So that's how we describe timestamps on data that we receive. But that poses all sorts of interesting problems around error, accuracy, and precision.
Right. I actually got a question from the audience that I was actually thinking about the other day as well. So it's a little bit off topic from time, but sort of in our database design, there's a big question mark about how to deal with missing values. Like, what's the difference in analysis, I guess, between a missing value and a value that's a zero? And sometimes there's if you're doing, say, roll-ups of data or histograms or something like that, it can be very hard to tell the difference, but it can be very sort of analytically important. So how do you deal with that in the database?
Yeah, that is very true. I think that that is often missed by people who don't do deep mathematics or statistics. That there are a lot of statistical methods that do not work well with missing data, and having missing data, like knowing that you're missing data versus not knowing that you're missing data, are different things. So in our database, we have 3 different data types that we support for telemetry data. One of them is text, which very rarely is used for anything robust. It ends up being, the git hash of a code release or something like that indicates some sort of punctuation point in a timeline. We have histograms, and then we have numeric data. And the numeric data, as much as burden as it was, it ended up being a pretty good idea to represent it this way. We support representing numeric data as 64-bit floating point, unsigned and signed 64-bit integers, and then some smaller, less precise types as well. But we also explicitly support null. So you can submit a value that is missing into the database. So you can explicitly, which is very different. For example, say you're checking a thermostat and you are unable to get the answer back from the thermostat, which is very different than neglecting to check the thermostat. And it's different for statistical. Like one of them implies an availability constraint, the other implies just a lack of attention. But I think that it's, and your comment in rollups, so once you've taken so for people who are unaware, rollups are used in general you're rolling up kind of, would say, continuous data. Obviously, all data is discrete in our computing environment. But when you start looking back over time, if you want to go back 7 or 8 years, it's rare that you would want to look kind of from the outside view at, microsecond level or millisecond level data. You kind of want to first zoom into hour by hour data, and then 5 minute, and then 1 minute, and then 1 second, and that sort of thing. So in order to assist performance of recall, it helps to materialize roll-ups of that data. So you take all the data that happened in, say, a 1 minute period. So you have a couple million samples that came in a minute for a specific sensor, and store some sort of statistical aggregate around that, say an average, the number of samples, a variance, perhaps a running derivative of that. And then with that, you can do fast recall. But if you don't have data in that window, it has some implications for the statistical methods you can apply to that. So I think the first step is acknowledging that and making sure that the data structures and the data types that you have in your database kind of acknowledge that possibility and can store, I took 35 samples in, 34 of them were numbers, and one of them was actually a null. And then it's kind of left up to later on the mathematician or the statistician, data scientist, whatever, to understand what that means for the particular method that they're trying to apply to the data.
Yeah, I think it's very important, maybe, more than some people realize. Just a quick story from back in the day when I used to program unmanned aerial vehicles. Whenever you would get a null, like the coordinates it would want to fly to would go to 0, and it would start flying towards the South Atlantic. So whenever a plane turned southeast, we knew something may be up. It would like fly away. So yeah, 0 and null, very different things.
0 and null are very different things, and I mean we learned that. We have in our analytics language, for example, which we call Cackle, Circonus analytics query language. We have like multiplication, division, addition, maxes, mins, averages, all sorts of stuff, and we have a class of those functions that are in the op class that operate on them as if nulls are 0. And then we have another set of all of those functions in our statistics package, which don't assume that null is 0. And it's really interesting when you're doing methods, depending on the context of the method that you're applying, you may want one or the other.
Yeah, definitely. I think it's on sort of analytics folks like me to maybe improve the analytics side of this, to be able to reason about nulls alongside numbers and things like that as well.
Especially when you go into some more advanced methods, like, for example, say you have a signal coming in and you want to do a discrete Fourier transform on it, right? So like dealing with null and missing data in a discrete Fourier transform is actually a really painful problem. But it's even more painful if you don't know that you have a null. So
absolutely.
I think being honest with your data and correct with your data is the only way to potentially be correct with your answers.
Yes. So there's a question from the audience, and I'm going to combine it with maybe some of the older questions, kind of along these lines of query. We're talking about nulls and zeros, but Well, firstly, can you maybe tell us the name of what your database is? We skipped over that, I think.
Sure. The database is called IronDB, and it's part of the Circonus platform.
Great. And can you talk a little bit about some of the time series specific operations, like in query, that IronDB provides? And I mean, maybe a little bit later, talk about analytics. There are several questions sent in about what kind of analytics do we support, and I know there's some pretty interesting work on analytics and time series. Sure.
So the types of things that we do, we really focused on taking. So in our terms of time series, there's a lot of different types of time series database. There are structured event databases. There are log databases where you have a timestamp and a log line that's unstructured. All of those kind of qualify as time series database. Ours is very specific in that we assume that you're monitoring a thing, and that thing is going to have some multitude of timestamp values attached to it, right? So say I'm in the case of like resource management and cloud computing, for example, I have a piece of physical equipment that's running a hypervisor, and it has a certain number of cycles that it spins in idle, in VM, in system and user. I have containers inside of that are spending CPU time. They're using memory resources. I'm monitoring each of those things, and I'm taking a measurement out of them at some dictated frequency. So maybe I'm taking a measurement every 1 second or so. And on the flip side of that, on more of a high frequency model, say I have an API that's driving my application, and every time I service an API request, I know sort of the endpoint that's being serviced. I know the version of code that's running. I know that the response code was, say, a 200 or a 500. And inside of that criteria, I have, say, 200,000 requests per second that I'm serving, and they are all taking a certain number of microseconds. So I have, for every single one of those requests, I have the timestamp and the latency that was observed on servicing that request. So those are the types of measurements we take in. So if we're looking at that, the types of analytics that we do end up being sort of windowed time. You have some sort of area of interest in time, right? So it's a temporal query that says, I'm looking over the last day, I'm looking over the last hour, I'm looking over the last year, year over year, that sort of thing. So everything has a time context. And in that, one of the challenges is you need to specify what you're interested in. So there's a search syntax that allows you to kind of drill down and find the measurements, or what we call streams of data, that you're interested in. So you may say, hey, I'm looking for latency on an API service in Amazon, US East, and US West, and I'd like to kind of look at them separately. So now you maybe have 10,000 web servers or containers in US East and 10,000 in US West, and you want to pull all of the latencies that each of those containers are providing and then compare them. Or compare the 99th quantile of latency over 5-minute rolling periods or something like that. So there's a specification of what you're looking for and defining the streams you're looking at. Say you pull out, say, 10,000 or 100,000 streams, and then you apply either vectorization across those, or you apply some sort of windowing across those, and then you apply statistical methods. And those statistical methods can be very simple, like, show me the variance or the mean, compose a histogram of all the values, and return the inverse quantile at 100 milliseconds. So tell me what percentage of the population is faster than 100 milliseconds. And then they can be more sophisticated, like apply an anomaly detection algorithm that looks at, a rolling seasonal average of these things, or an exponentiated weighted average, and then try to do some sort of predictive analysis to bracket expected behavior and tell me how likely the next data point falls in that, right? So there's a huge range of incredibly primitive kind of time series centric functions that you would apply, and then you kind of cobble those together and build more and more on those to provide, to produce more complex and usually domain specific questions that you would ask on the data.
So we talked a little bit about query and analysis. We talked a little bit about sort of time representation. Can you talk about how those things interact, right? Like, so the design itself of the database, you know, how did you design the storage and say roll-off or reindexing and things like that to accommodate the types of queries that you think your users are going to do?
Well, I would say that a lot of that is built out of 7 years of discovering workloads that we found to be unfortunately unexpected. So there's a lot of evolution in the database design. So one of the recognitions that we had early on was that when we're receiving data from systems, those systems are pretty much the definition of relentless. They don't care if your database is down. They're still going to produce the data. And as previously mentioned, a lot of the statistical methods don't apply well if you're missing data. So you can't kind of just ignore data when you're down. That means that if you're down for, say, 5 minutes, when you come back up, not only do you have to keep up with the current workload, you have to ingest the previous 5 minutes of missed samples. You have to catch up and then play in real time. So it becomes critical that you don't go down ever, right? You have to be able to basically read the data off the wire. You have to be able to ingest data. And the data structures and I/O patterns for optimizing that are very different than the ones that you would use to do sort of instantaneous recall and analysis of that data, right? So I think that most people can agree that the fastest way to write data to disk is to not care where you write it and just write it. So you kind of write to the end of a file or write a new block, the next available block. Ideally, if you're using, with modern storage, it doesn't matter so much that it's sequential, but if you're using large storage devices, it helps to write large sequential blocks, have large block sizes on file systems, or not use file systems at all. But the idea of writing these large chunks of data out, it's pretty clear that you've written all of this stuff as it's come in, and it's not organized in a fashion that allows for incredibly fast recall. So it's not put into columns for doing vectorized crunching, and it's not correlated by stream or by time or by, we have a multi-tenant environment. It's not correlated by account, right? So using a database format and on-disk structures that are optimized for uninterrupted ingest, we have to realize that those structures are not the same that we want to use for doing immediate recall, and they're probably not the same that we want to use for doing long-tail analytics over multi-year data sets. So we accepted that and then realized that we needed to do ETL between those things. So we have certain data formats that are used depending on the data type for ingest, and then others that are used for doing sort of interim recall over extended periods of recent time. And then we have long tail storage, which is stored in yet a different format that is optimized for read-only recall. Not strictly read-only, but it is incredibly painful to write to and delete, for example. But it's highly optimized for storage, compacted storage size, and like vectorized crunching. So I think that the idea that you could have a general purpose data structure in there ignores the fact that economics are a real thing here. So if I'm going to store a petabyte of data, and storing that all in like non-volatile RAM or NVMe just isn't economically tractable. So I have to be able to kind of handle all of the different I/O workloads that are against affordable storage types and map that into the requirements of the database.
Kind of expanding on this economic issue a little bit. You know, whenever you talk about storage, there's always a discussion about economics related with storage, right? Like, you know, the picture of the storage landscape, I guess you could call it, has changed dramatically definitely over the past, 30 years since I've been in the business, but even over the past, say, 10 or 5 years. So I guess, can you speak a little bit to how the original economics of, say, spinning disks versus, even tape is used nowadays still, versus, say, solid state devices or, cloud storage or something like that? and how that influenced your original design, and how you've evolved the design with the changes.
Well, like any good startup, I will say that before we had our own database and decided to build one, we actually built this as a Postgres, like an altered Postgres backend. Actually kind of similar to the way Timescale works. And we found that to be wholly inadequate for what we wanted to do and where we thought the trajectory of the input data was. So we ended up taking everything that we learned in that and building this system. And at that time, I mean, that was 2011-ish. SSD was expensive, but available, and spinning disk. I mean, we were still working with like 5,400 RPM drives and 7,200 RPM drives and 10,000 RPM drives. Like, there were differences between those, both from a power profile and from a cost profile. So we were trying to optimize this, and we kind of carried a lot of the learnings. There were some publications around hierarchical storage and CFS that we learned from. But what we realized was that the cheaper the storage we could use, the better, right? We are talking about an epic amount of data here. So ideally, if we can get it done with the cheapest storage possible, we do that. And then when it doesn't meet operational requirements, we try to carve off small pieces of the application that don't meet those on that slow storage and upgrade them to faster and faster storage. And as sort of time progressed, I would say probably around 2014, 2015, the storage market started to heat up in an innovation realm, right? So SSD kind of became available in the cloud from a point and click point of view, right? You could just say, I want this much or I want that much. Then NVMe, persistent memory, all of that stuff. The memory architectures and buses changed. So the way that you could deal with data changed fundamentally. So what we do now is about every 6 months, we kind of look at the innovations that have happened, which tend to be a little slower than 6 months, and then the pricing changes that have happened, both from the on-premises point of view and from the cloud point of view. And we say, okay, this is the new landscape. Do any of the decisions that we've made in the past no longer make sense? Most recently, I would say that the one thing that has become clear is that a lot of the data structures that we use for indexing the names of things. So imagine you have a billion things in your system that you need someone to say, oh, I want this 1,000, or I want this 10,000 of them, or I want this 500 of them. And their queries are arbitrary. They tend to be multifaceted. Imagine having a 10,000 column database where you need to index every column of that to be able to do your searches. We obviously don't do it that way. We have a different in-memory architecture for that. So we use kind of a layered set of adaptive radix trees and bitmap hashes and things like that, and some hash tables. We were able to take those, and instead of building on-disk formats for those, we were able to make those data structures pointer invariant and backing store them against fast storage. So that was one of the things that I don't think we could have done 4 years ago, that we are now able to do, given kind of storage innovation and the cost around that.
Right. So this is a little bit diverging from that topic, but it's still on the question of value and price. So there's a question about, we had said that, you have to equate the justifiable cost of storing data with the cost that, it takes to sense it. But the question is about, is the value of the data itself, should we take that into account? So like the future value of any analytics of the data, or the inherent value of the data. And, we thought about this a lot in sort of the security realm, because data does have an inherent value. So when you're trying to protect something, the amount of protection you put on it should track with the value of that thing, right? So in the same sense, like does the database itself, should it have some awareness about the value of data?
I'm not sure if the database should have an awareness of the value of the data, but I would say that if you can quantify the value of your data as non-zero, it's almost a no-brainer to store it, at least in some fashion. The real trick is that a lot of data has value that is later realized, and that value is only realizable if you have historic data. So there's a lot of data that it's very difficult to say, oh, I know this data will have value. But when you come to realize that it has value, having a year's worth of that data or 7 years worth of that data is immensely valuable. So anybody in the SRE realm knows that every time you have an incident and you go review what you're doing, you become smarter as an organization and individually. And you're making hypotheses, right? You're making scientific reason. You're executing scientific reasoning around the data that you have to say, hey, I saw this pattern, I saw this correlation, I wonder if this is causal. And if you can say, let's go back and replay the incident from 3 months ago, and you actually have the data, then you can compound that value, right? That organizational growth compounds. But it doesn't work if you weren't collecting the data before. So I know it's a meme to say monitor all the things, and it is sort of unrealistic to actually store every piece of data. But the closer you can get to that, the more future value you can generate out of effectively thin air.
Yeah, I mean, that makes a lot of sense. Yeah. So go ahead.
I was going to say, one of the tricks that we use, I mean, we do a lot of like the standard tricks of compressing time series data. So there's a paper by Facebook around the gorilla techniques. Those have evolved quite a bit. I'm not sure they've evolved at Facebook. I'm sure they have, but they've evolved in the industry. So there's a lot of hybridized techniques. There's some structural compression techniques that people use. But some of the other techniques, so one of the techniques that we kind of hinge a lot of our value around is the idea of taking 1 million samples a second and saying, after some period of time, say a month, we're going to store all 1 million of those samples, but you will no longer be able to figure out where inside the second they happened. So instead of storing 1 million samples in a given second with, like nanosecond offsets or attosecond offsets, we store a single histogram for that 1 second and store all 1 million values in that histogram. Right? We introduce time error, we introduce value error, both bounded very tightly. But it turns out that most of the statistical questions that you would ask doing analysis are achievable via that data structure. And now you've taken, basically probably a half a megabyte of data and compressed it down to less than 1 kilobyte of data, right? And it's a lossy compression, but those techniques preserve the ability to statistically query the data. So there's some fascinating approaches that you can use that say, hey, I don't know if this data is valuable, but the cost of storing that data can be so cheap that I don't really need to ask that question critically.
Yeah, and just a comment, I think this is one of the coolest things about working with databases and database design is that one second you're talking about how much it costs to store a bit on a disk, and then the next second you're talking about analysis and histograms, and they're completely they're intertwined and related. So kind of along those lines, there's a question about that's related to storage. This question of what are the things named, what are the names in your database? And I think there's a related question about, if you do have this long-term storage that we're talking about that enables this analysis and data value, in today's environment, basically nothing is, quote, real anymore, where, an IP address represents, one machine 1 second, and then next second that same IP address is a different machine. And inside that machine, even there's virtual machines, and inside virtual machines there's virtual environments. So everything's virtual at every single level. So how can you enable us to do good analysis on sort of longitudinal time series data when you sort of don't even know maybe what this IP address is? If you make a decision to store everything based on IP, you're obviously losing a lot. So do you have any thoughts on this analysis question that does relate to long-term storage?
So I think it's critical that there's some fundamentals of monitoring that are incredibly important. So when you are monitoring something, it is critical that you monitor the simplest thing. if you look at the outside of your house or your apartment and you've got a water meter or a power meter, the power company does not monitor the watts per second that you use. They monitor the total number of kilowatts consumed. And the reason they do that is because if they miss a measurement, they still, given the mean value theorem, have the average that you used over the longer period of time, and it's still correct. So it's important that you monitor things correctly and that you actually take reasonable values that have good that are good inputs to mathematical processing. Given that, one of the things that you need to consider is that you need to have data that's mergeable, right? So if I track latency by API latency, for example, that's one of my service level objectives, is to have a certain number of my requests below a certain latency threshold, and realize that I may change that threshold over time and still need to be able to do analysis. I need to make sure that the way I record that on a single container that may come and go is the same as I record it on all the other containers and all of the other services, and that I can merge all of that together to get a holistic whole world view. But by tracking it on each individual container or serverless process or what have you, I can drill down into those, right? So I can see individual containers. So like a classic thing is I have a Kubernetes cluster that's running, say 20 nodes, or 20 containers and pods and things like that, right? So I may deploy a new piece of code that spins up 20 new ones and turns off the 20 old ones, right? So all of the names of my telemetry streams will sort of change because they'll have different container IDs and things like that. But I can still query those and say, hey, guess what? I don't actually care about the container ID, right? I want to find all of the things running this application from this time to that time, ignoring the container ID, merge them together and let me look. And then I see the overall trend and I can say, hey, there's a bump there. Does that correlate with anything specific? Hey, break it down by container ID, right? So one of the classic things that you'll see is that, it's not classic, I will say one pathology of failure that you see that's not uncommon is that you don't have a degradation of service that's homogeneous across a set of machines. You'll have one server that's malfunctioning, one node in a cluster of systems that you believe is homogeneous actually is acting very heterogeneous, right? It has packet loss that's unexplained. It has a noisy neighbor that's causing it to have latency outliers that others don't. And if you don't track things on that sort of granular stream level, there's no way after the fact to actually prove that point out, right? So you can say, I have these weird latency outliers. I have outliers in my app. And it turns out, no, I don't. I have outliers on specific containers in a cluster at certain times. So now I have a very different hypothesis around what's happening. So having that data both on an individual granular stream level and having it rolled up into a comprehensive view kind of lead to the right question and answer analysis that engineers need to do.
Yeah, and I've been thinking a lot about sort of meta-analysis of the pipeline, if that makes sense. And I think maybe some of the things you're saying kind of go along with that. Cool. So this question is not really related to the last one, but I'd like to hear the answer. Do you have any advice for people working with timed data? Maybe not someone that's using a dedicated time series database, but do you have advice for people looking to index that data, store that data? I suspect you have some experience with that.
Yeah, I mean, I think that the classic database approach to indexing is always valid in that you index when it's required. So you should be able to brute force your answer. If your brute force answer is computationally cheap enough and both economically and computationally and time-wise and everything that meets your constraints, then you shouldn't be indexing. There's no reason to maintain an index for that. And if it's not, I think that in traditional databases, it can be a little tricky sometimes the indexes really don't map themselves. They don't graft onto the problems at hand. At least that was our experience. So the types of indexes that we use in our system to describe when there is activity on a stream and what the names of the streams are. So for some context, in our system, It's very specific to our system, but we have the idea of, it's a multi-tenant environment. We have an idea of an account. So you have an account number, say 12. And inside that account, you have namespaces for metrics or streams, and those are UUIDs. And inside those UUIDs, you have multiple streams. Say you have a temperature gauge that says, it's called temperature. And on that temperature gauge, you may have multiple different facets, right? You have a temperature for the thermostat in this house upstairs and on the main floor, and you have one for across the street on the upstairs and the main floor, and you have it for the apartment down the street. So you have a lot of different streams that are separate. So you have basically namespaces at the account level, what we call the check level, which is this gross UUID namespace. And then on the metrics, you have an arbitrary set of key value pairs or tags. So like maybe zip code or street number or floor level or square footage size of a house that may be attached to that thermostat. And all of those things are valuable. And you may want to be able to query on all of those. So the idea of saying, I actually think about, so the way database indexes work typically is that you end up having, it's hard to index every single column of those, like zip code and square footage size and all of that stuff, and combine them rationally. So it requires different data structures at times. But if you're just starting out, the easy thing to do is don't index, run the query and figure out why it's slow, and then add the optimal index for that specific query and kind of iterate on that. It's a pretty good pattern.
Cool. And, along the indexing question, so there was a question from sent in about, how do you decide when to re-index? How do you decide when to do, I guess, and a similar thing would be rollups, and maybe can you talk a little bit about, the re-indexing versus, rolling something up?
So in our system, we do not roll up anything based on materialized queries. So I'm pretty sure that, and I could be wrong here, I'm happy to be corrected, but I think that there are some databases like InfluxDB in particular that allow you to specify a query in the database that sort of materializes itself. I believe that's for like complicated queries or expensive queries. They'll end up materializing as the data arrives, and you end up getting a very fast read side because you've kind of stored the answer already. That's a different type of roll-up than the types of roll-ups that you're typically talking about in like telemetry databases, where the types of roll-ups that we do are, hey, I'm getting a million samples a second on a stream, and I need to be able to do, say, I want to know the 99th percentile of queries in January, right? So that's a million per second, 86,400 per day, 31 days in January. That's a lot of data points. And I need to be able to answer the 99th percentile or 99.5th percentile. And I need to do that in interactively fast, say 100 milliseconds. So the rollups that we do there are really taking those extremely long vectors of doubles or unsigned 64-bit ints and turning those into something that is statistically accurate for macro questions, statistical questions. So like, give me an hour-by-hour average or an hour-by-hour variance. So we're doing rollups that basically materialize those loosened granularity over time. I don't know if that sort of answers that question. Yeah,
no, I just think the interplay between sort of like pre-analytics or whatever you want to call it, cubes or realized queries versus indexing is a pretty interesting question.
Yeah, so we've aimed, and this may be folly on our part, so we've aimed in our database to make all of those cubes and interactive complex queries fast enough to do interactively that we don't materialize them. So if you have, say, 10,000 streams that you want to do, day over day, 7-year correlation on, our answer is just do the whole query. Don't materialize it, just do it when you need it. Because chances are your query is going to be wrong anyway, and you're going to have to redo it. And if you've materialized it, you're going to learn a couple days from now that's not actually the query you want to do, and you're going to interactively modify it. So if you don't have a database that's fast enough to do those kind of like really large aggregate queries interactively, then you're just punished as a data scientist. It means you have to like really think about the query you want to run, and then codify it and materialize it and then rely on it. Whereas I think that the idea of powering ad hoc data science is much more powerful. So we focused there, both on the search indexes for metric names and tags, being able to kind of arbitrarily specify Boolean expressions and regular expressions around the nomenclature of streams that allow you to kind of refine a billion stream data set down to the 400 or 500 or 10,000 that you're looking for, or 2 that you're looking for. That needs to be interactively fast, like 1 millisecond, 2 milliseconds to be able to perform that query. And then being able to pull the time of data that you want. So typically, coming back to one of the questions before about the analytical functions that we provide, basically everything that we do requires a start time and an end time. So even if you're looking at a current value, if you're trying to look at a predictive window on that, you say maybe you're taking 4 weeks of data to do your prediction, you need 4 weeks of data. If you're looking at 10,000 streams and you need 4 weeks of data, you need 4 weeks of data for each of 10,000 streams. And you need to effectively, in our system, you would need to map and reduce that across the cluster and then do something reasonable with that data. So ideally, we map and then we reduce as far as we can for the statistical processing that would happen afterwards. But optimizing for those queries, the idea is that you should be able to do that in a second, or ideally, I mean, I won't say we achieve 200 milliseconds. That would be my goal, is a 200 millisecond interaction. That way you can basically run those queries as you're typing effectively. But our queries aim to run those large queries in less than a few seconds.
Cool. So there are 2 questions about geodata. So just in general, I know like a lot of time series sources also have geodata with them, like cell phone or something like that, obviously. Do you reason about geodata at all, spatial data in IronDB?
In our current database, we have no spatial data in it. So I would say that in our current system, and I think there was a sort of an offline question that was about when do you kind of build a database versus using an existing database, and when do you use 2 databases? So I would say that this relates to like when do you use a graph database and a time series database, or when do you have to merge them together? So for a geospatial database, if the geospatial activity is related to the stream of data, meaning that all of the samples in that stream have the same geospatial coordinates, for example, like on a thermostat or something like that, then coupling it with another database is a pretty reasonable approach. But if each sample had its own geospatial coordinates, I think it would be intractable to try to couple that. It's too ingrained into the data itself, and it's kind of fundamental to the internal processing of the queries. So you'd have to build geospatial support into the database. Our current use cases for our database do not have each individual sample having a different, longitude, latitude, altitude type of thing. So we don't do that. If we did, we would have to integrate that into the database, and we would probably build custom indexes. And of course, in our system, we would probably crib off of the work of PostGIS to kind of see how those indexes are built in their stuff and do papers research on the digital library and ACM. And then we would figure out how to build an index for that data. But we don't have a use case for that today.
All right, thanks. I think we have time for probably one more question. So I'm going to throw one out there for the data structure nerds out there. You talked a lot about conflict-free replicated data types as sort of a low-level data type structure for storing this data. So those data types are also used in some form in configuration management, like Git, or say a shared document system. Can you compare, contrast your CRDTs with the ones that are used in Git, and
yes.
What's the difference here?
Yeah, so I mean, I think the most elaborative CRDTs, I'm sure that CRDT experts are welcome to dispute and disagree, but I think the most elaborate ones end up being around document coordination. So the simple case of that, and I'm trivializing it, is that you have a long string which multiple people are editing, and sometimes they cannot talk to each other while they're editing, and you want to make sure that they converge on a consistent outcome that does not surprise anyone. That's a very, very hard problem. It turns out the ones that are mathematically correct, like provably correct, sometimes aren't the best ones because they introduce surprise to the end user. It's not actually what they want. Like, it can guarantee a consistent outcome. It's just not the consistent outcome I want. Those are really challenging problems. The beauty of time series data that we deal with, which is like numerical samples observed over time, is that it's easy to define the input set and the data structures that we use as very simple CRDTs. So the space of CRDTs that we use, the most complicated one we use is a last right wins set, which is used to replicate naming for stream data across a cluster of systems. So if I want to attach tags to a specific class of metrics, I need to be able to attach them, and every node needs to agree which tags are on which sets of data. So we use an LWW set for that. We have our own implementations for that because our database is written in C, and most of the existing implementations out there are not in C. So we wrote our own. But the data structures for doing numerical CRDTs are rather simple. So if you imagine I have a timestamp, like an attosecond granularity timestamp where I've observed a value. In reality, I should never observe two values at the same attosecond. Like, one, we can't observe things at attosecond level anyway, as in our current state, like humankind. But there should never be two samples at that point. So if I do receive two samples at that point, it's not unreasonable to just say, hey, the one with the largest absolute value wins, right? And that turns out to be a CRDT that's ultimately convergent, happens to be idempotent as well. So all of the inflow of data that we have has been designed very carefully to only accept data that has idempotent commutative transactions on it. And if you're saying, if you know what that stuff is, if you don't, look it up. It's fascinating stuff. But if you're looking at that, you're like, well, then you've only solved the easy problems. The answer is exactly, right? We very specifically tried to distill the database problems that we solved to the easiest problems possible. We limited the product scope around that. And then we were able to build an incredibly reliable and robust system because the underlying data structures are not complicated for that.
Great. So yeah, I think that's about all the time we have today. Be sure to check out the ACMQ case study that this talk was based off of. It has a lot more information about Circonus and IronDB. Theo, I'd like to thank you again for your informative presentation and insightful answers to the many questions. Sorry for the folks that we couldn't get to your questions. There were like literally 50 or 60 questions. We couldn't get to them all. But thanks to each one of you for taking the time to attend, participate, and send in questions. This talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. And also, if you could fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen. And on behalf of the ACM, Theo Schlossnagle, and myself, Chris McCubbin, thanks again for joining us, and I hope you will join us again in the future. This concludes the talk.